I'm Hurriyetoglu. I work in Wageningen University and Research, Wageningen Food Safety Research, the institute. We work on artificial intelligence and data tools to support the EcoReady initiative for understanding the impact of climate change and biodiversity to the food security. I will. This is our team, and many of the studies are led by different people. We collaborate as teams of 3-4 people in line with the aims of the project. And I will present use cases. First, I would like to provide details of the observatory, a bit more concrete information about this part. And next, I will talk about how what kind of AI applications, what kind of AI methodologies we are using to make the observatory as useful as possible using big data. The observatory is based on big data architecture. We need to process a lot of data. It should be real time. It should process big chunks of data. So therefore, we developed for this purpose, we implemented a big data infrastructure that can process data in multiple modalities and present these data in a uniform way after a lot of pre-processing and processing and analysis in the observatory dashboard and in the mobile app. In the mobile app, we have additional functionalities like games, like gamification, news articles. On the dashboard, we have a chatbot. We are developing it at the moment. It has traditional tools for us to understand the data. I will provide the links to it, and please visit and tell us about your opinion. We designed the observatory via workshops. We invited policymakers, citizens, farmers, industry actors to tell us what they would need this tool for. And at the end, we have the design in line with their needs. This whole architecture, the stream of the data, presentation of the data, processing of the data, all should follow certain principles based on the concerns of the stakeholders. So they could share data or use data responsibly, or they would know when they cannot use the data as well. So this clarity helps everybody. We are developing an ethical infrastructure, a detailed one, and it is coming well. These are the core principles and supporting values, and all these are identified in communication with the stakeholders, with the whole consortium. So what is important, what is useful, what is what we can tolerate or not. All these aspects are evaluated so we can have a governing structure for the observatory. We have the Living Labs. Living Labs has been providing us a lot of good input. Data is one of the tangible one, but they provide us about their opinion about how the observatory should look like, what kind of principles, ethical principles are important for them. When we talk about, when we give them the word about the sharing or ownership of the data, they are quite enthusiastic to contribute to this topic because it is their own data and they want to see the possibilities of both protecting and exploiting data or allowing other users to understand what they are generating. It has been quite good collaboration with them. Um, we have collected quite good uh, amount of data from the databases that are available. Sometimes they are not in a format that you can put in a database or query it. So we did a good amount of work there. So in a uniform way, we can present the data. We can benefit from this data to create AI models, to present it to people who want details. One example of them is chefs. I will talk about its details later. So therefore, I am going a bit quicker here. Finally, the observatory should be the uh, collector or the overview of the EcoReady project. Uh, each work package will provide input to it. The information generated, these webinars we are in, um, terminology, the planning tools from other work packages, work package 1, policy suggestions, policy recommendations from work package 5. So everything should come together to have a coherent system that can support researchers, citizens, farmers, and policymakers. I talked about this. This is the long URL for it. If you go to the EcoReady website, you will see it as well. We have quite many screens. I would be very happy if you could go there and explore it, see how it is useful or not for you. We mostly focus on Europe, whole Europe. Some use cases are restricted to the regions for the living labs or based on the data availability. So therefore, we cover both the whole Europe and local or regional information as well. And this is one of our strengths. This is the mobile app optimized for mobile users. It is not the mirroring of the dashboard. It has additional features that would allow engaging citizens, informing them, collecting feedback from them, and it is being improved. Here are the QR codes if you want to store them, or from the website of the project, EcoReady project, you can find this information as well. I can accept 1-2 questions, if any, before proceeding with the data and AI tools. Okay, so I have a couple of use cases. I want to share them with you. We have a comment or a question by Alejandro Rodarte.
Yes, good morning. I'm trying to turn on my video, but it's not turning at the moment. I'm Alejandro Rodarte, Director of Food Safety at Food Drink Europe, the European Association for the Food and Drink Manufacturers, and always difficult, but nice to find time to learn about the projects and work being done in terms of improving our food system and the risk management. So I'm very interested in the work package on policy recommendations, and maybe it would be dealt at later in the presentation, but if you already can tell a little bit of which are the policy makers that you're targeting with this, from which commission or member states, or a little bit more on this activity, if you can.
I can give a short comment on it, and then I would refer to work package 5 people. They are doing it. To the best of my knowledge, and actually in our activities or when we work with them, we have a generic definition of policymaker. Like GRC, we start with GRC, Joint Research Center. They are contributing to our consortium actively. We meet them in our meetings monthly in average. And even at the very beginning, before the workshop we did for the requirements elicitation, we talked to them like, hey guys, you have a lot of information. What is missing? So just not to replicate each other or to know really what are the pain points. They provided us a good input. This is the EU level, and we keep asking them if they have any comment, if they have any connection we can talk. This is the first line of really the primary communication. Next, the municipalities, like from local governments via the living labs, we ask them like who from the government, from agencies you can reach and get feedback, or uh, what kind of format or timing would be needed for these policies to be formulated, or where this is the second. The third line, work package 5 people really doing good work in following the policy making cycles. So they know uh, what is discussed, when it is discussed, and they work on it in detail, which I really don't know much about. But those are the clues I
Yeah.
collect and I could say.
No,
Did it
that's
help?
already very interesting. I would add something because indeed targeting the right policymakers is it's crucial for to bringing this the results that can provide a little more real info of what's happening in terms of climate change and threats for food security. I would put it very clearly. For example, if the DG Sante works with the member states and in technical working groups, deciding on risk management measures on all types of contaminants, and this list is growing bigger and bigger and bigger. And for us stakeholders that are in the practice, they need to comply with with new regulations and also for enforcement, it becomes more and more difficult to give proof of the impact of climate change, for example, or different geographic variations on the increase of certain contaminants. And usually, uh, if an EFSA conclusion says there's a risk for health, then sometimes it goes a little bit too straightforward. And those results brought to the risk managers really dealing with the Commission's DG Sante in formulating those risk management measures would be extremely helpful.
I'm. We will have work package 5 seminars in this series,
Mhm.
and these are the really the people you need. So,
Yeah,
uh,
I
and
will
if
be happy to connect with them and provide feedback and also be updated on policy recommendations to give our take on
this
how.
would be really helpful. We have been trying to get input from farmers as well, from industrial partner actors like you as well. So therefore, your input will be quite valuable. Thank you.
Welcome.
So I will start with a bit more data and more intro part, like what's artificial intelligence, what is data. So to have a framing about what we are doing, and then the rest will get easier. So therefore, maybe here we can have space for more questions. Uh, Most of our group worked on this. It is the EFSA database. EFSA published their monitoring from countries as CSV files. Um, Over years, these CSV files are many. They may be used in different um, taxonomies. Slightly, it may differ over years, and you need to track it if you want to have a longitudinal study. The format may be really tricky to put all together because of the number of the products and the contaminants and the countries. And the sampling is different as well. So uh, with all these challenges, having these CSV files make it almost impossible to benefit from them. We tried to benefit from them, we could not, so we had to solve it. We harmonized the data. We could have it in a uniform database, and we can start to understand trends or pain points of the food safety in Europe, with being careful about the sampling. So we analyzed a couple of trends, and it was how is the chemical contaminants are based on each product, and how it can be sometimes it is affected by the targeted monitoring, sometimes it is affected rarely, but we have a model for it uh, from bigger trends like climate change, and we documented those in the respective publication. Please have a look, and it is open source. It is on. We have the GitHub repo for it, and more. You are more than welcome to comment on it. All data is really there, so we tried to get some main trends, main conclusions about this big data set. What is more observed, what is less. Again, these numbers are affected by what you are looking for. So if you don't look for cadmium, you will not find it. Or if you don't sample, some countries will not see it. So therefore, it is quite tricky about interpreting the raw counts. And we see one of our success is to identify this kind of biases. And we know where to warn people. So everybody knows data may have issues, but what kind of issues? So we revealed those. The countries may have been tested for something more, or it may, in a regular check, it may you may observe some of the contaminants more than others, and then you can be more careful about it, or you would test more for it. So this is the data, and many of our data comes from this kind of setups, or we collect it. It is biased and small. So we need to understand the data as much as possible so we can understand how our conclusions solid or need additional checks. So for the artificial intelligence, so what we mean by artificial intelligence, it is a broad field. Historically, it has been dealing with planning, all supply chain aspects, for instance. It has heuristics, it has ontologies like knowledge representation. A lot of additional aspects are under artificial intelligence. In these days, it is understood a bit more like machine learning, a bit more deep learning, even like foundation models. So we are operating mostly in the machine learning area with by trying, or in some use cases for deep learning, and certainly in these days foundation model, because it already has the information for you to build on. In the classical machine learning, you have your features, you have some control on them, you know what is going in. You have your algorithm to optimize your decision boundary, and you have the prediction. So it is a bit more manual, and you optimize it, you clean it. In the deep learning, it is a bit more cryptic. So the algorithm actually, this part processes your input, and you only see the output. So the layers in your deep learning model have this information, and it is a black box to you. So how would you trust such a model. Maybe you cannot trust, so you don't use it in high-risk environments, but you can use it uh, for predicting big data and get the trends, not a sample-based decision, for instance. So how does it work really? When we mean machine learning, we have labels on the objects, and the algorithm or black box or feature extraction uh, go and see the color, whether it has a leaf or the size or the shape. Those are the features that are extracted either a bit more manually in a classical machine learning setup, or deep learning just gets whatever it can get. And it draws a decision boundary, like if it is long and yellow or green, then it is a banana. This kind of uh, decision boundaries are created. When you have a new sample, um, it tells you whether in what class it is. And this is the maybe a starter definition for machine learning. We have one problem, a problem that gets a bit bigger with deep learning. When it is a black box, you can't understand why this prediction is yield. So if you are a policymaker, a regulator, how can you trust this decision? It is not 100%, or you don't know. So we use, my Zoom, yeah, my Zoom window just interferes. So here, when we analyze images with small differences, the decision changes based on superficial artifacts. So it is understood as a horse when it has this label. If you remove the label, it is not recognized as a horse. Same for this car. So this kind of examples make your system unreliable, especially if you are making a big decision based on single prediction, and when the statistic is not that much relevant. So you need to really understand whether this guy has COVID-19 or not. But if your model make the prediction based on some label, then you should not use it there. And you should try your system for this kind of samples as well. You should evaluate it, validate it. One way of it to have one by one tests of your model, and always you can use explainable AI. So it tells you what is really based on what features it is making the decision. Here, these are the features it is using. And you have heat maps or salience scores for each feature, then you understand which features play a role in the final prediction. So it requires calibration as well at the end. Here I will present you one small, it is not small, but my presentation is short, study about using this chef's database. How would you really incorporate additional features that are demographics, environment, policy, a lot of information you can find, combine it with chef's database and see if you can predict mycotoxin in grains or toxins in grains. Our input information is chefs and yearly or tabular data about geopolitics, about import-export, about the climate, like precipitation. You give all these features for each year. This is better to see and really understand whether it is increasing or decreasing, or what is affecting. As a, like, in a hunt for causal relationship, you can see with this model what affects the decisions, what feature becomes the most important. Is it the precipitation? Is it the import export? Is it the politics? So you give additional features. Those are the additional features you give, and you have the raw data, and at the end you can see what's happening about food safety for a certain product or for a certain contaminant. You can understand with some AI optimizations. It is a lot of work and optimizations and double checks, but at the end you can really say whether grains has more risk or less for a given year. This kind of model, when you apply it on temporal data, you can start to predict this year before the official numbers are collected, for the following year with less certainty, but with some usefulness. And by using the SSPs, projections for climate or society, then you can make projections for many years ahead, or you can rank the risks. The explainable AI tells us like what is affecting this problem. The Human Development Index is one of the highest. The temperature is the second highest. Agricultural stress is third highest, or a bit less, but still impacting. So you have a rank of what is important, what is affecting some problem, especially when you have this combination of temporality, a combination of all these features, so they are in the same bucket to be ranked or ordered. Yeah, those are the main ones. So any comment or question about this study before I can go to the following one? And the algorithm is XGBoost. This is a traditional algorithm, not deep learning. Okay, so I will talk about the pest observations as one study, and then the time will not allow to go all over of them, so therefore we will need to do something. Anyway, with climate change and biodiversity differences, we are having a change in the pest behavior. So, and this, we observed some pests in different regions. We don't know where they will appear due to the climate change. They have unknown number of generations to us. So normally we know how many, or some farmers know their pests in their region, but it is changing what they will do, when they will appear, when they should use pesticide. And this is particularly important. Pesticide use should be minimized. So it is food security issue as well. You should be as intelligent as possible to be able to say, okay, this particular pest is may appear due to this kind of weather pattern and time of year. So then I should be more attentive to this, maybe informing the farmer, training the farmer, or just warning the farmer. Or as a police regulator, you should expect that some sort of pesticide may be observed, so you do more controls. So it is helping us. We need to know better. We worked with domain experts here. Uh, we always work with domain experts to validate the data, the input, the output, the interpretation. But this time it was a bit closer collaboration. I will go over this because we needed the data to be collected, the communication with the farmers. They provided us exactly what they know from their domain knowledge and what they don't know, what is new information. Because our model may be just dummy to them, so if they know uh, from their domain expertise. We used the weather information because we had this information at the moment, and observations of the farmers. So the farmer goes to the field and say, I observed this particular pest. And when we combine this data, those are the observations, and over time, those are the alarm is ringed, and these are the farmer when the farmer goes and check the data. So we don't have many data. Over time, we improved our data collection significantly, but this is the first version. This is how our input weather information looks like. And we need to match these input patterns to the observations and see if there is any new information. We use the crop, the period that the crop is active. So a certain month of the year. And our data is mainly yes or no, like they went at a certain date to the field, and if they see it, they say, I observed this pest. And then based on the information we know about this pest, so how long it requires for it to appear, and after appearing, how long it will be active. So it is a time window. We labeled our weather information and trained our machine learning models. We applied many of them, but I will focus on the decision tree. At the end, a decision tree works when you don't have when your data is small, when your data is imbalanced, like positive and negative are quite different, the ratio of these observations, and when your data is not periodic. So the farmer doesn't go to the field every week on Monday, and make an observation. And if they don't see some pest, they mark it. If they don't see it, they don't mark it. So there is an ambiguity. So the only algorithm that worked in this specific use case was the decision tree. And we could get rules under what features, and it is quite explainable by itself. The decision tree I just showed is converted to this kind of rules and presented to the experts, and experts found it useful. So they could see some additional patterns that is not in their system. And we used clustering as well, clustering of the weather information, and it is really showing certain clusters have the observations. So there is information, it's possible to identify it. If you collect better data with the time series capable machine learning algorithm, you can do better. This worked even with 29 positive observations. And I will show this to you in the rice example, and we are updating the previous one as well. When you have data collected over many years, we are trying to do this for Europe at the moment. You can, and you see how the climate changes for each different weather variable characteristic, like maximum temperature, minimum temperature, and wind speed. This kind of features. So you see it is changing based on a weekly calculated normal. If you use a bit more traditional, it is still deep learning, but traditional classical deep learning, let's say, LSTM, you can get the pattern. And you can have an RMSE of 185 hours. This is hours. And you can really predict what will happen in the field, because you have the weather information, a historical one, and you have the observation. But can we do better than this? So this is the pattern predicted. The orange one and the blue one is the original data. So it is almost there, you know it. So what if we use foundation models or deep learning models that capture a bit more information? Here, the challenge is to encode this information in your model, this time series characteristics, for instance, or many pests has you have data from about many different pests, and how can you create a model that benefits cross pest observations? So and then at the end, I should be able to make a prediction for a pest that I don't have training data for. So this kind of benefits it has when you use foundation models and deep learning like TimeGAN. And we use this to create synthetic data, like how whether a certain weather pattern cause a pest. So the generative AI generates a prediction for you. And using this as a training data, improves your performance. And this is on a different use case. So therefore, the RMSE is different. We want to mostly understand, in many cases, to understand the causal relationship as well. So what is affecting it? So we can maybe take some measures. I will show it in the seafood later, or just make sure we rank the risks. Here, the maximum and the minimum temperature for 9 points in a time series, how they are effective, they are shown. And then you understand before how many days your prediction is the best. Yeah, I will just continue from here because it is there. Any comment or question for what I have told until now? I would like to just go over crop yield prediction because the time management will not allow me to cover everything. And this is a bit more traditional, like I will mention a couple of information. If you use satellite images based on their NDVI vegetation index, you can really understand where is the crop, whether it has any risk, and over time you can see the changes. That is it for now. Um, our colleague Shinshin led this study, and she had quite good results. Yeah. At the end, you have the each segmentation, like field segmentation, and after this, you can estimate the crop yield for a certain year, and then create the real information, because official numbers are sometimes not accurate or they are aggregated. So you may want to get into detail. Yeah. Next, I would go to the tetrodotoxin contamination, a study we recently completed, and it is being reviewed. Here, the problem is to understand whether seafood contamination with tetrodotoxin is happening. This is a work we are collaborating closely with the regulators. So regulators need to know as soon as possible when they should close fields for seafood. So it can't be so too early, it can't be too late. So you should use as much as possible information. Official information is being published about the water temperature, about weather, about chemical results, observations. So using this information, we want to warn the regulators as soon as possible about the risk. Based on this information and some other information they may have, they will make the decision to close the field or not. The time series aspect is really important, and we make use of it because it develops. It has a reason, uh, and we try it. Sometimes it is not affecting the results that much, but in this study, we found the time series of the weather information, the measurements is really affecting with some additional information. Yeah, at the end, our model was validated to be quite accurate. We tested on a separate year. So this means when we use all data to train a model, we can make predictions for the coming year, for 2026 or 2027, using SSPs like climate projections for years ahead. And again, it will be great. I don't know if we will achieve this, but for Europe, a seafood monitor would be great. This is weather information. This is based on weather information, but we have another study that uses satellite images as well. And again, we will see if it will be possible to benefit from all these features. When we look at the importance of the features, sunrise and how many hours of sun was available and sunset time are really affecting whether you will observe tetrodotoxin or not. And here we have a good ranking. And based on this, we can make predictions for the coming days when we know how much sunrise and sun hours. Actually, the model will be doing it, but at the end, this is a validation as well that our model, that it makes sense. The model, the predictions are reasonable, so it can be used. We are working with domain experts, and they are quite happy to see this some sort of validation, or some of the information is known to them, but some not. Yeah, this is the tetrodotoxin contamination. I kept telling you that we can use SSPs, projections about the society, or the politics or the weather for doing forecasts for years ahead. And this is one of the example studies in this line. And the last one doing this as well. Like the overarching aim is for EcoReady is to make forecasts for policymakers. It is mostly years ahead. We have been progressing as well in this line. Again, this is in preparation for publication, but we can provide a summary. In the data-based approaches, it is mostly you don't have the domain knowledge. You don't know the global trends, or you can't really embed all climate, temperature, economic politics in the same model. So you need to work with a domain expert to validate it, to be very careful. But how it can work for years ahead? Maybe the world will change. You don't know. You don't have this information in your training set. The other side of the event in magnet, in domain knowledge, in economics, there is quite good amount of information about what is happening, what may happen after some sort of another event. So they really know what is happening in the markets, and they have more validated, hard-coded, domain knowledge-based systems. And they can create predictions based on some disturbances. If COVID-19 happens, what will happen? If the tariffs in the US are in effect, how the economy will be shaped, whether prices will increase. This kind of scenarios modeling is possible with magnet or similar models. So how can we merge them? Is it possible to combine them and get best of both worlds or not, or under what conditions? So this is an exploration of harmonization of these modeling approaches for some better result or quicker result. One of the problem about traditional models, it takes time to collect their data, to get their feedback result, and it is not, if the system is big, it is maybe not very easy to understand why a certain prediction is generated. So therefore, we use both systems separately and in combination to see what is happening. So I explained this. We focused on a certain subset of the variables magnet using. Those variables are compliant format-wise with the AI, like in a tabular data. They are not cyclic, for instance, or it is straightforward to have them. Some variables are formulas in magnet, for instance. So they use a couple of different variables. So we focused on a subset and used this to predict wheat production, because we had the wheat production as well. And we did this for multiple scenarios. What happens if, like I said, some disruption in economy happens? How magnet looks like? If Western people, our colleagues from economic research were here, they could tell it certainly better, but I will try my best. All information collected at country level, sometimes the per capita income, the food prices, the demand, the productions for each agricultural crop, um, and the consumption in addition to import and export. So all economical relations related to food are taken care of. They are included from official numbers, from GRC, from databases that EU prepares. So based on all this information, they can generate scenarios. If something happens, if we lose biodiversity that much, the food stress will be that much. So this we have magnet models in the observatory, LCA life cycle assessment as well, and we will be using them in any case for understanding food security under climate change and biodiversity loss. But here we are after making things maybe faster because magnet results comes every year. Uh, so you can't just say, okay, I want to try multiple scenarios, or you can't update it in the middle of the year. So you need the information from all 2025 so you can do your calculations. So just we wanted to make things quicker or more hybrid, both data and domain knowledge. Even the occupation of the land is taken into account. So we focused on this information, this cycled one, a subset, as I mentioned. So what is SSPs? Those are the projections about like what will happen in coming years for certain countries, how much it will change if we continue like this, or if the climate temperature increased 1 degrees in average or 2. So middle road versus extremes are all has a different SSPs, SSP 1, 2, 3, 5. There is up, I know up to 8. So there are quite detailed scenarios, and you can use them as like the simulation of the future or expectations of in the future. So we are in the middle. We are using the middle of the road one, but it is quite easy to use others as well. If things get more hard, if the climate change accelerates, or if some privacy, some policy change affects something, then you can change it and make your calculations, projections again. So based on some shocks, what will the wheat production, can AI really generate it for us? And we have these two models. Magnet has its own result, and based on this subset of the features, we have a production for the AI model. And here, the input and output of the magnet can be compared to AI, and it is feeding the data of the AI. We have the paper for it, all details. If you are really curious about it, I will be happy to discuss it further. I talked about this variety of the data. We used XGBoost. It's quite good for tabular data. Based on this input data, can we predict wheat production? Yes, the model could learn the pattern, and we can run this model quite quickly. If some of the information from here is updated, you can just press the button again and get your number quicker. And you don't need to wait for the magnet until 2027 to give you the number. We can get the results per country. So we can have the policy recommendations per country, or a municipality in a certain region can come and see what is happening to them under what conditions. We have the possibility to understand now, given we have the AI model, we have the ranking of the features, which one is more important or affecting the wheat production than others. And we have the temporal, those are the magnet results, they are bigger. And we have the AI results. Here, over years until 2100, we have the correct ranking. So the technological development is not taken into account here, but here it is taken into account. So this is the explanation of our colleagues from the economic research. So it is a bit less problem to have them at different scales. The most important thing is having the ranking in parallel to each other. And this is for multiple SSPs. So this is another country example, and we have using domain knowledge, now we can, and even a subset, we can quickly generate, update the results about the feature of the wheat production. And this helps all the warning efforts or policymaking efforts. Any comment or question? I will continue to the last use case. It is a bit longer, but I will try to finish in 20 minutes so we can have a bit more time. So the observable, when we say climate change, it is really tangible. So we know it is increasing. And how it affects the number of the disasters, under what pattern it creates food security risks and food safety risks altogether. So when we talk about climate events, they are mostly about extreme ones and combined ones, compound ones. And using SSPs will allow us to use projections about the climate and understand how in the future, based on the frequency of the climate events, how the food security will be at risk and whether it is accelerating or not, or in what region it is more a problem. So when two or more extreme climate events occur, we call it compound event. The combination of extreme events actually increases the effect, and this number of combinations are just increasing. The combination and not just the extremes, when they are combined, they are really harmful to the whole system. So these SSPs, these scenarios, these disruptions in the food supply are really affected by the the disasters being combined. And climate change increases the number of these events. Food security and food safety are interconnected. If it is not safe, it is not food. So they are interconnected. And if some food is contaminated, but by flood, contaminants, hazards are transferred to the fields, then you don't have anything to eat. or it affects the human health if you tolerate it. So therefore, they are closely interconnected. Um, Many studies has put it in the uh, those are the available studies focusing on food security, and this is our study. So we analyzed all these studies and we identified the relations. Again, it is the study that is being reviewed. What kind of disasters cause what type of hazards? Like heavy metals are uh, connected to heavy metals in food are connected to the extreme precipitation. Bacterial pathogens are connected to heat waves, food or flood, and extreme precipitation. Mycotoxin is mostly connected to drought. So we have identified a certain um, pattern, and this allow regulators and us to really go and check for something. When a flood happens or when some heat waves comes, we should go and check for these two, for instance. Heat waves will cause less heavy metal related problems. Yeah, I will go over this. So it just gives us a fine-grained information. If we can create an AI model for it, like I showed in the explainable AI perspective, we collected information of the disasters, like how many disasters happened, the climatic data, like weather information, where it happens, how it happens. So we could at then get the relevant with relevant satellite images and combine all of them. We got the yield information as well for mice. And so this will be our variable to understand whether crop yield will increase or decrease based on disasters and climate information. We are incorporating all possible information we find, like the available water capacity. And if hydrology experts have a database about water capacity, we make use of it. And Santiago, our researcher, our colleague who is doing this, has a background in hydrology, for instance. So we just combine all possible information. This is the advantage of using deep learning and multimodal uh, variant of it. Uh, it just combines all this information and tells you what is important. We have the satellite images as well for and it's over years, so we can train on particular years and test on other years. And we have the mice production for all these years, so we can see if there is any relation. For crop characteristics, we have other type of databases, so we collected them and put them in the same place to be processed. Yeah, this is per region so it is not country, to be clear, per region. And this is really what at the very beginning of the EcoReady project, when we asked the GRC people, hey guys, what is you are doing, what you have, what you would love to see, but maybe hard or tricky in your setup. The most prominent thing, one of the most prominent things they said is the regional information. They need regional information. They said they have everything at country level. Like they don't need anything. They are officially required and they do collect uh, data at country level, but they don't have regional level data. So therefore, in most of our studies, we do our best to do our work at region level. By region, you can think it as a province, but it is a bit more flexible. statistics offices has different type of data collection when you think the geographical features. And we have the water capacity, and we will see if it has any effect. So combining all disaster information, actually we harmonized it. At the end, it should sit in the same database. You can imagine it as in the same Excel file, and then you can use it or compare it. This we did this, and it is in the observatory, actually being put in the observatory. It is from an available database, but bringing all this together in a useful way was our work, actually, like the chef's database. Next, this is the status until now, like what happened in the history. But we want to see what may happen next year, the year after. What are the regions under risk? So therefore, we use SSPs, the projections for climate, and it is very easy to calculate or run the model for all SSPs. So you can test different things, or if in a couple of months you see, oh, we are not going to do SSP2, SSP5 will happen, then you can just use these results. So when you combine all this information in a model, and this is the really beauty of the deep learning, classical machine learning can't do this in a single model. When you can't do it in a single model, you can't see the ranking across these features. So therefore, it is a beautiful deep learning model. Everything is together. Still, it is black box, but we will see into it in using explainable AI. And we are seeing at the end whether the mice yield will increase or decrease. Those are details I will rather not go into. Just to say, like, we use satellite images as well until now, and how the world changes in response to disasters is being taken into account. Yeah, those are the experiments and the variants we tried. One of the contributions is to see, I tell it like it is intuitive, but it is not actually. The combining of the information isn't easy for some type of models. It is more easy for some particular models. And finding which model is actually optimally capturing all this information together is one of the tasks. So here, attention convolutional LSTM did a good job. The number of the parameters is more. So being able to take using multiple parameters without distorting the patterns is a real challenge. So this model was the winner. So we used this one after now on. And we tried multiple models. Sometimes when I say like we used SGBoost, this decision comes from a couple of trials that are sometimes not very explicit. So we have ground truth, and we use data from certain year for training, and another data from another year, same data, but for another year for test. And then we measure the error rate. And then we optimize the hyperparameters of the model, or we decide how big the model should be. So these specific SSPs, SSP2 4.5, for instance, and we created the projections for between 2030 2039. And you can do it for many other years as long as you have the SSPs. So now we can see the future. You have the historical data, you have the SSP supported data, future projections, and you can see what change it may happen. In a table, it is more processable. You can process it, and we have the chatbot, chat agent, AI agent in the dashboard that does it better. But for the human eye, you can start to see patterns like in the future, this region is under risk, or these regions are getting risky in the future for certain type of disaster. We have it for different for all. We just got after you have all this set up, it is just a button you press for different setups or countries or regions. Our ultimate aim is to have it for the whole Europe. We succeeded to have it, and we are very proud about it. And it will be on the dashboard. We are now in the process of just integrating it. And these differences are really explorable based on a policymaker and industrial actor can come and see what's happening. The model, the AI agent may combine data and say, hey, this food will be risky, or it will not come from there anymore due to this and this. And this crop differences has implications on the prices as well. Although magnet model can do this better, we can just provide the information for an expert eye to be interpreted. We have country level results. We can say which country is more at risk for what reason, and their ranking, like which country will be affected less or more. I mentioned these parts. Having information beforehand is useful. We have in work package 1 output, the real magnet output. We have disruptions or changes based on the policies. Our own results are not based on policies, but policy changes may be taken into account in combination with domain experts. It is an early warning system. So here we can say which policymakers in what countries should be really concerned about this particular problem. Farmers has their own forecast, whether under what conditions they will have the problem, or what they can grow, or it will be risky to grow. Yeah, this is our next steps, just incorporating more information. The chef's database is not integrated yet, but we hope to do it after we have first versions in the on the observatory. So that is all, and I think it is good timing to have some discussions if you want. If you have any questions.